in the last part of the lecture, I want to now talk about the third generative model, which we call Kronecker Graph's generative model. And this is a very different model because it will be kind of much more mathematical, in some sense much less interpretable, but it allows us to generate very rich networks. So let me explain what the Kronecker Graph model is. So the way we will think about this is we'll think about it from the viewpoint of recursive graph generation, right? Can we think of network structure recursively? And in particular, can we generate networks that have this type of self-similar structure, where the object is self-similar if the object is similar to a part of itself, like the whole has the same shape as one of its parts. And the idea is that we would be able to then generate big graphs from small building blocks, right? And in this way perhaps imitate different communities and growth of different communities. And the Kronecker graphs will allow us to do this through this notion of a Kronecker product that will allow us to generate self-similar adjacency matrices. Right? So the idea will be that if I start with some starting graph, I somehow recursively expand this starting graph into bigger and bigger graphs. So I want to have a small kind of generator, small building block, and then I want to use it to generate bigger and bigger graphs. And the way this will work is I will take a small generator matrix like the one I have here, let's call it K1, and then I'm going to apply Kronecker product to itself. So I'm going to do K1 Kronecker product K1 to get now a matrix K2. And then, I can keep multiplying and I will get this very nice self-similar structure. Now let's say, that has size 81 by 81. And just notice that K1 has this pattern of, ones kind of along the diagonal band and zeros off the diagonal. And notice how now this adjacency matrix also has same structure, right? I have this block of zeros and then I have this block of ones. But each of these blocks is similar, has zeros off the diagonal and kind of has non-zeros on the diagonal. And then each of these blocks is again similar to the original block. So that's kind of what this Kronecker Graph's model will allow us to do. So now how do we define it? How do I get what I just showed you on the previous slide? We are going to define the Kronecker product of two matrices A and B the following way. So the idea is if I have two matrices A and B and I Kronecker multiply them, then basically the way to think of this is that I take the matrix B, I put it into every cell of A and multiply with the entry in that cell. So this means I can take two matrices, A and B, that have different sizes, and the Kronecker product of them, the size of the Kronecker product will be the product of the sizes, right? So if matrix A has n rows and matrix B has k rows, then the number of rows of the product will be n times k, and the same for columns, right? And the way you see now, the product is simply you take B and you put that entire matrix into the every cell of matrix A and multiply with an entry at that cell. So now that we know what is a Kronecker product of general matrices, we can define a Kronecker product of two graphs by simply as a Kronecker product of the corresponding adjacency matrices, right? So now that we have defined this, this basically goes here, right? I have a first adjacency matrix. Now I do Kronecker product of this adjacency matrix with itself, and I get this type of structure, right? I have 0 here because if I take K1, put it here and multiply it by 0, I get a 3 by 3 block of zeros, while in these other parts, I get simply a copy of K1 because I have a coefficient 1 here. So basically, now I get a matrix of size 9 by 9, where I have two blocks of size 3 by 3 of zeros, and the rest are simply copies of this matrix K. And now that I have a 9 by 9 matrix, I could Kronecker multiply 9 by 9 with another 9 by 9 matrix, and I would get a Kronecker matrix now on 81 nodes. So I have now a graph on 81 nodes. So How are we going to define Kronecker graphs? Kronecker graph is obtained by a growing sequence of graphs by iterating Kronecker product over this initiator matrix K1. So if I want to get the kth Kronecker graph K, I'll simply take my initiator matrix K1 and I'm going to Kronecker multiply it with itself m times. So basically I'm taking the nth Kronecker power of the initiator matrix to get the final graph. And of course, nobody says you have to take one initiator matrix and just power it with itself m times. You could have different initiator matrices and multiply them to get a bigger graph. So there's a lot of flexibility here. To give you an example, here is an initiator matrix on 4 nodes. Here's the corresponding graph. Here is the adjacency matrix. Notice basically we have self loops on the diagonal, and then kind of first row, first column is basically the star node linking to other satellite nodes. If now I generate a Kronecker graph with this initiator, here's the adjacency matrix, and again notice the self-similarity pattern. Here's a different initiator matrix with the corresponding adjacency matrix, right? Again, I have this node that links to all other nodes, but then there is a triangle here as well, denoted in this part. And now notice as I create a Kronecker graph, I get the same self-similar structure, right? I get basically a band of non-zeros. I have these two elements that are 0, corresponds to this area here. I have this part, corresponds to this part here, right? So you see how I get this recursive self-similar structure where basically this initiator matrix is its structure is retained at different levels. And this is how we define the Kronecker graph. So far, we have defined Kronecker graphs as deterministic, right? We started with a 0, 1 adjacency matrix and we generated a bigger adjacency matrix. So what we want to do next is we want to make these Kronecker graphs stochastic. We want to make it so that it generates random graphs. And the way we generate random graphs with Kronecker graphs is that rather than thinking of the initiator matrix as a little graph, as a little 0, 1 type matrix, we are going to think of it as a probability matrix. So basically, rather than having K1, we are now going to have theta 1. And rather than K had either an edge or no edge, now we will say that every edge has a probability between 0 and 1. So theta is now a matrix of probabilities. Then we are going to take this theta 1 and we are going to apply Kronecker power to it. We are going to Kronecker power it with itself to get the kth power. And then now that we have this probabilistic adjacency matrix K, we are going to sample edges from it at random according to the probabilities defined by this in this matrix. So let me basically give you a picture that will explain what I mean. Right, so the idea is I start with some initiator matrix. The entries have to be between 0 and 1 and they don't have to sum to 1. I Kronecker multiply this initiator matrix to get a bigger probabilistic adjacency matrix. Now every cell here can be interpreted as a probability of an edge. So in order to generate the graph, I now simply traverse this matrix and flip a coin where every entry tells me what is the bias of that coin. And if the coin says yes, if it lands on on head, then we actually create a graph. We create an edge in the graph. And we then call this is now an instance sampled from this probabilistic adjacency matrix. Right, so the idea is once you have this probabilistic matrix, you simply go and flip the coins according to the biases that are encoded in the values of the cells, and this will give you a graph. It will give you now an instance of a Kronecker graph sampled from this stochastic Kronecker graph. This is great because now we can generate graphs stochastically, but all having kind of similar structure, all being generated from the same initial probability matrix. What is the problem? The problem is that we have to flip all these coins, and if the graph has size n, which means this matrix has size n by n, then we need to flip order n square coins, and that's far too many coins to flip if I want to generate a million node graph, because then I need to flip million squared nodes. So it would be, I have to flip 10 to the 12 coins. Or if I want to generate a billion node graph, which is, nothing too large, then I would have to flip 10 to the 18 different coins, and that's unfeasible in practice. So let me now tell you how to do this faster using what is called a ball dropping or an edge dropping mechanism, and it's quite cool. So here is how we are going to generate Kronecker graphs faster. So think that you have this 2x2 initiator, probabilistic initiator matrix that has, entries A, B, C, and D. Now, if you Kronecker multiply this with itself, the Kronecker product matrix will look like this, right? The first entry will be A times A, then it will be A times B, B times A, B times B, A times C, and so on. Right, so that's one way to look at it. Is basically, first you would generate all these cells and then you can flip the coins. But what you can also notice is that we have this kind of hierarchical structure, right? I have A, B, C, and D, and then each of these four quadrants has further A, B, C, D in there, right? So the way you can now think of this is as a two-level structure. And the way you can say what is the probability of a given edge, it's simply you can basically separate it out as a set, almost like as a dropping into the underlying adjacency matrix, where at every stage you have to decide which of the four quadrants do you want to dive into. So let me give you an example. If this is my final, this is my final adjacency matrix size I'd like to create, so this would be number of nodes is whatever is the number of rows and columns here, then the way I can think of it is I can split this into four quadrants and I can say, A fraction of times I'm going to go into this part of the network, B fraction of times I'm going to go here, C and D. And then basically you can pick, again, according to these values A, B, C, and D, one of these four quadrants. And now that you have picked it, you nowadays say, I have now picked this quadrant, let me again split it into four parts, and again let me pick which of these four different subparts do I want to dive into. And you would pick one of them. And now you are still not all the way down at the bottom of the matrix, you still have to choose which cell you go to. So again you split this into four, and again decide which of these four to pick. Right, so what this means is that basically rather than flipping these coins kind of row by row, you start at the top and then you descend into one of the four quadrants with probability proportional to A, B, C, and D. And you pick one of them and move into that part. And now you say, I have four ways to go to, and pick one of the four ways at random, and you'll move to the one part. And then again you say, now I'm here, I want to go deeper. And you keep descending until you hit the individual cell, and this is when you stop and you put an edge. This means that you are going to land in a given cell exactly with the probability according to that cell. The only difference is that you may get a couple of edges colliding, right? You may land to the same cell multiple times. If that happens, just ignore it and try again. And this gives you now a very fast way to generate a Kronecker graph, right? So basically this edge dropping or ball dropping mechanism basically says take the initial matrix, whatever are the entries, normalize them, and then keep dropping keep descending in until you hit an individual cell and put an edge there, right? Put a value 1 there, and this would mean that you have connected nodes I and J that are in row I and column J. And if you do this, what is interesting is that, for example, with a very simple adjacent parameter matrix, only 4 values, you can actually generate the graphs that correspond to real graphs quite well. Here is, for example, this is now a directed graph, in degree, out degree, clustering coefficient, diameter, which is number of nodes at a given distance. These are some other properties that people care about, and you can notice how Kronecker graphs in green and the real graph match really well, and all you have to do is decide on these 4 different parameters, right? 4 different parameter values. So basically with just 4 parameters, we are able to generate realistic graphs using Kronecker graphs. Here the network we are trying to mimic has 75,000 nodes and more than 500,000 edges. So the cool thing is now we are also able to model degree distribution, clustering, as well as shortest path distribution, as well as some other properties with just 4 free parameters. Here are the numbers of those parameters. If you start with this initiator matrix, you can basically generate this social network on 76,000 nodes and 500,000 edges. So to conclude the lecture for today, the summary. So today we looked at these traditional generative models for graphs. First, we discussed about what metrics do we use to characterize the graph. And we talked about degree distribution, clustering coefficient, the giant connected component, as well as shortest path length. We started with the simplest possible generative model called Erdos-Renyi random graph model. And we saw that it generates shortest path lengths realistically, that it gives us connected graphs, but it doesn't generate clustering coefficient. So we then talked about the small world graph generator, and we talked about how you only need a couple of random shortcut edges that bring down the diameter but keeps the clustering high. So this is what was in the significance of the small world model. And then we looked at a different model called Kronecker graphs that's kind of more mathematical and is defined based on the Kronecker product of graph adjacency matrices. We then defined the stochastic Kronecker graph where the adjacency matrix is stochastic, and we can then generate multiple instances from the stochastic matrix. We talked and then last about this ball dropping mechanism that allows us to generate Kronecker graphs quick in a fast and efficient way, so we can generate graphs with billions of nodes without any problem. So with this finishes the lecture for today. What we are going to talk about next week is about deep generative models for networks, right? So while today the models were kind of mechanistic with a lot of insight from the network generative processes that happen in real world, on Tuesday we are going to talk about deep generative models, where basically we will say, let's just formulate this as a machine learning problem, as a kind of complex prediction problem, and all we care about is to generate realistic structure, and we don't care so much about whether what is the true underlying, let's say, real world generative process. So we learn how to generate graphs from raw data.